Alright students, so today we'll be discussing about the lanthanide contraction or the lanthanide contraction. This topic is very simple, it's confusing too, but it's also very important. So without further ado, let's dive into it. So very quickly, let's take a look at our purity table and see where our lanthanides are. So as you can see, it's from your lanthanum to your lutetium, from your atomic number 57 to 71. We will also be looking at actinoid contraction, since it is very similar to your lanthanide contraction. The only difference in the case of actinoid contraction is that in the case of actinoid, the structure is more complex. So that's it. So anyway, let me also show you the picture on how the size decreases here. So as you can see here, from your lanthanum to your lutetium, along the series, it decreases successively along the period, along the series, yes. And this lanthanide contraction is interesting for the fact that it decreases successively without any abnormalities. So as you can see, the lanthanum has a atomic radii of about 103 picometer. Alright, and all the way to lutetium you have 86.1 picometer and so on. So the decrease is dramatic, it's huge and without any abnormalities. So we'll be diving into the definition here very quickly. So as you can see, lanthanide contraction, it is the gradual decrease in the atomic and the atomic radii with the increase in atomic number. So along going from left to right. So we'll be discussing about the reasons too. Here I've mentioned the main reasons. It is due to the poor shielding effect of 4f orbitals. But as you keep on studying this lanthanide contraction, there are some confusing parts which I will also discuss. So you listen here very carefully and let's try to understand what this lanthanide contraction is all about. Okay. Not forgetting about the graph here, if you will. This graph is atomic number plotted against the atomic radii. It's measured in Armstrong, so you can see here lanthanum you have about 2.7 Armstrong, all the way down to lutetium you got about 2.2 Armstrong. You can also see a steep decrease in the end part of this series, not an abnormalities I should say. Okay, so let's understand the main reason behind this contraction. It says here it is due to poor shielding effect of 4f orbital. So very quickly I'm going to show you what shielding effect are. And so shielding effect is basically the shielding of outer electrons by the inner electrons from the nuclear charge. Now to understand this, I want to bring out an analogy for this. And so let's say you are a celebrity and you went out for shopping. Now as you go out with your bodyguards for security purposes. And say a guy try to approach you and try to ask for your autograph, but guess what? In crowded place, the bodyguards always protects you, and so the bodyguards is going to push the guy back away. All right, from not allowing you to take autographs or whatever, if you will, right? And so it's for the other publics that are trying to approach you, but the guards are going to push them back away just like this. So this particular effect is what shielding effect are. If you take an atom here, you see the nucleus here. The nucleus here are attracted to all of these electrons here. These are the bodyguards here. So it's the outer electrons here. The nucleus attract even the outer electrons. While attracting the outer electrons by the nucleus, the inner electrons are going to push back the outer electrons when they try to get closer to the nucleus here. It's called the electron-electron repulsion. As you already know, electrons are negatively charged particles, so when they get closer to one another, opposite charges, they repel each other. So this particular effect, the inner electrons here are pushing back the outer electrons away from the nucleus, and this particular kind of shielding in the inner electrons by the inner electrons is what's so called the shielding effect. Alright, but also note this: if you have more electrons in the inner shell, that will also mean you have more repulsion, so there is more shielding effect. But also you have to consider something. If the inner shell, the size of the inner shell is big enough and far away from the nucleus, just like in this case, there will be less shielding effect. The proton here can attract the outer electrons more easily, since there will be more gaps, if you will, so to say, figuratively speaking. Alright, so these two particular features about the shielding effect is really important to understand why our lanthanide contraction is contracting, so to say. And so one last thing about the shielding effect: if you have a poor shielding effect in the inner shell, which will mean there will be more attraction of the outer electrons by the nucleus. So in this case, if the outer electrons are being pulled towards the nucleus more, then in effect the atoms will become smaller in size, and hence contraction. And so let's take a look at the poor shielding effect of the 4f orbitals. And so if you have a cerium here, atomic number 58, you have 58 protons here, and you can see these are your innermost shell where your 1s, 2p, 3p, and so on resides, the electrons. And let's say this one is your 4f orbital, the 5d orbital resides here, and the 6s orbital resides here. So in the case of this, you have 2 electrons in the s orbitals, so 1 and 2 right here, and in the 5d shell, 5d orbital, you have 1 electrons, and in the 4f orbital you have 1 electrons here. So 58 protons are going to pull the outer electrons, and they're going to pull these 6s electrons, the 2 electrons, this and this, towards itself. And if you take a look at the fact that the 4f orbitals is very far away from the nucleus, there is going to be less shielding effect or poor shielding effect. And so the proton is going to pull the 6s electrons, the outermost shell, without any hindrance. And so the overall changes in the size will be contracted, the cerium will be contracted, and will have a smaller in size in reality. So is the case for the lutetium. As you can see, the atomic number increases, 71. So you have, in this case, you have 2 electrons on this. The outermost electron are the 6s electrons, and you have 1 electrons in the 5d orbital, and 4f. In the 4f you have 14 electrons. 8, 9, 10, 11, 12, 13, 14. So there are more electrons here, but considering the fact that the 4f orbitals are very far away from the nucleus, again, still, the 71 protons are easily going to pull these outer electrons, these 2 6s electrons, more, and hence it's going to even pull more as compared to that of the cerium here, and it's going to get even smaller in size, more contracted than that of the cerium here. Also, it's important to note that the shielding effect of 4f orbital, the shielding effect of 4f orbital on going from cerium to lutetium increases, since there's an increase of electrons from the 4f orbital from cerium to lutetium. So here is 1 electrons in the 4f orbitals, and on going from cerium to lutetium, you have 14 electrons in the case of lutetium. So more electron density will mean there is more shielding effect. So the shielding effect increases here. This is important to note, since if there is more shielding effect, you might think that the size will not be contracted. But the fact that there are here in this case 71 protons, which is a lot, as much than 58, and due to the fact that the f orbitals are very far away from the nucleus, without any hindrance, the 71 proton pulls the 2 electrons in the 6s orbital very easily. So in other words, you can say the increase in the size of the proton, the increase in the number of protons, bypasses the shielding effect of the, even though there is an increase in the shielding effect on going from cerium to lutetium. So in conclusion, gradual decrease in atomic number and ionate radii with an increase in atomic number. So this is due to the poor shielding effect of 4f orbitals, since 4f orbitals are very far away from the nucleus. Alright, so I hope you understand something from here. If you have any doubts, you can always message me. And also I want to give you an assignment for this. So for the actinoid contraction, it is still the same. It's just that the inner electrons are in the 5f orbitals. So I also want you to write down the reason behind the actinoid contraction, and also compare this actinoid contraction and lanthanide contraction, and see whose contraction is even more contracted. All right, thank you.